Immer noch. Please connect to the same network. Können Sie etwas sehen oder nicht? Please connect to the same network as this Mac. Choose Zoom Mac Pro. Das ist einfach, das geht nicht. Bildschirmsynchronisierung. Können Sie irgendetwas sehen?
Ja.
Ja,
Ist es scharf oder unscharf?
unscharf.
Also unscharf, aber da diese Synchronisierung ist scharf.
Ich sehe alles, ich sehe sehr unscharf. Mal schauen. Jetzt ist es gestochen scharf, oder?
Ja. Mhm.
Okay, es scheint jetzt zu funktionieren. Das war ein ganz anderer, sind andere Arbeitsschritte, als ich vorher hatte. Ich verstehe es nicht, aber egal. Wir probieren es, okay? Jetzt mache ich hier noch meine, nein, die mache ich nicht mehr zu. Okay, let's switch to English. Right. So, I hope I manage to explain after all these technical troubles. So that our topic is the exactness properties of the tensor product. And the last thing I explained was the following. Maybe I recall it. This was the proposition 2.9. So I have A modules and an exact sequence or a sequence. And the statement was this sequence is exact if and only if for all P A modules, the related sequence, the dual sequence, if you want, is exact. Okay, I think this is okay. Okay, so this we proved, and this is now very useful for showing the following proposition. We had it already, but let me repeat it. Okay, it says that the tensor product is right exact. So if, okay, if I have such a sequence, exact, let's give it names F and G. If is exact. Okay. And N is any A module. Then this tensor sequence is also exact. So everything is now tensored with N. So this map, of course, is F tensor the identity of N. Maybe. And here I go to N2 prime tensor N. P tensor identity on N. And here it goes to 0. Okay. So the proof, actually, this is what I, oh my God, I want to change. Strange. No, okay. Why not? Not loss. Okay, the proof. Okay. So using this, maybe let's put the star here. Using this equivalence, the proof is quite elegant and easy. Okay. So I start with this exact sequence. Okay. And then what I do, I apply, okay, this property to the following module, to hom np. So here, okay, so I can show here, instead of, I have p, but instead of p, I put here hom np, because that's okay, because this holds for any A module. Okay, so if I do that, then I get this sequence. Okay, everywhere I put hom np, and here hom m, and here hom m prime. Okay, this is exact. But the point is now that last time, okay, a lemma, maybe I should have repeated, but right. But we know that this is canonically isomorphic to this module, hom m2 prime tensor np. So this is a canonical isomorphism. Do you remember that? So this I can do everywhere. Okay. So this is exact. Actually, this sequence is essentially the same as this one. Okay. So this is exact. Good. And this is exact for all p. Okay. Exact for all p. So therefore, I can again apply this general observation, this time backwards. Okay, I go this way, and I get, therefore, so this is backwards. I see that this sequence, okay, now the directions are again reversed. This is exact. Okay, so.
Can I ask a question?
Sure.
So in the fact that you're passing from the first hum sequence to the second one,
Yes.
You're kind of using the fact that the natural isomorphisms that they like commute with the other maps.
Yes.
Right. So is that basically because this isomorphism, it's like a natural isomorphism of functors?
Yes. Yes. Yes.
Okay.
Yes. Yes. I think. Yes. Yes. I think. I mean, you would have to see. I mean, you would have to see what is this map doing. Okay, it's completely not natural. Then you see what is this map doing, and you just rewrite. I mean, and then you see it. Okay, but in a way, yes, because all these isomorphisms are completely natural. This is what you get here is what you expect to have. But maybe you check yourself.
Okay.
Okay, but this proof is in a way is quite neat, because if you want to prove, of course, one can prove directly that this is exact. Okay, so what I mean, on the one hand, you have to show that this, okay, you show that this one is surjective. It's very easy, but the exactness here, okay, one can prove it. But this way, it's kind of elegant. Okay, it's kind of but it's no big deal. It's no big deal. Right, but the problem is that you lose this injectivity. Okay. Okay. Injectivity. Okay, I should write here. I said this already. Okay, I said injectivity gets lost. So that's why let's move on. We lost so much time. So those modules N for which you don't lose the injectivity, those have a special name. These are the flat modules. An A module N is called flat. It's a strange name, huh? It's flat. if for all injective A-linear maps, okay, so you have M prime to M injective, let's call it F. The tensor product is injective. Okay, it goes from M prime tensor N to M tensor N. Here you have F tensor identity N. Okay, this is a bit unreadable. Right. This is injective. Maybe I better put this here. Right, so this notion of flatness is quite counterintuitive. So I think it's not something that is so easy to understand. I think it was introduced by Serre, I believe. Serre. Maybe I should check. Right. So I don't think it has a very simple geometric meaning, but if you do this, these kind of homological algebra proofs, it's exactly what you need. It's exactly what you need. And we will see in a moment that the free module is flat. Yeah. Okay. So, right. So I have this little proposition. It's very simple. So it says that a module is flat. A module N is flat if and only if tensoring with N preserves exactness of any sequence. Okay, for any sequence. Okay, so for any A module N, equivalent or, okay, 3 conditions. 1, N is flat. I just defined it. 2, okay, short exact sequence. It's a lot of lighting, this homological algebra thing. If this is exact, then the tensor sequence is also exact. Okay, is exact. And the third condition is says, okay, same thing, but instead of a short exact sequence, take any sequence. Okay, tensoring with N preserves exactness of sequences. So, okay, so we say tensor N is an exact functor. Okay, so there is not much to, I mean, this I stated for the sake of clarity, but there is actually not much to prove. Let's see. From 1 to 2, okay? How do we prove that? So the way we define flatness is we say injectivity is preserved, okay? But the other property is clear anyway. So if you see, if I don't have this, I forget about this part of the sequence, then we know we have already the right exactness. Right exactness is always true. Okay, the only property that we need is that the injectivity is preserved. Okay, so if this guy here is injective, this guy should be injective as well. And this is the definition of flatness. So in a way, it's clear. Okay, no, it's not clear. It's by the proposition 218. Okay, okay. Otherwise, please let me know. And from 2 to 3. So if you assume we have this exactness is preserved for short exact sequences, then we know it for any sequence. This is just by splitting up a long exact sequence into short ones. This is by splitting long exact into short ones. Okay, I think please check yourself the details, and from 3 to 1, this is trivial. Okay. So there is not too much information here. So first, I mean, one class of examples of free modules, flat modules are the free ones. So any free module is flat. The free A module N is flat. So maybe this also explains that you haven't encountered the concept yet in linear algebra, because if we talk about vector spaces, we always have this flatness. So proof, right, it's very easy again. So let's assume I have an injective ring morphism, F, or you want to call it F, goes from M prime to M, the injective. Okay, then I take a basis. I know a basis exists because N is free. Let Pi be a basis of N. Okay, so now let's see. I take an element in my tensor product, like let's call it Z. It's an element of M prime tensor N, okay, which I assume is mapped to 0 under F tensor identity. Okay. I need to show that F tensor identity is injective. So I need to show if I have this element Z must be 0. Okay. Okay, so every element in the tensor product can be written in the following way. Okay, it's a sum over the indices xi tensor vi. So this, and the xi is unique. With unique xi in M. Where is it? In M prime. Okay, this was what we proved about the basis in free modules. We have this unique representation. And then I map it, f of z. Okay, let me see. Where is it? Now I map this thing. So f tensor identity of z. By definition of the tensor product of maps, this is this, f of xi tensor vi. Okay. And now I know this is 0. Okay. But now, okay, in which now I'm in M tensor. Now this takes place in M tensor N. Okay, and I have this representation. But again, every element here has a unique representation in this form. I also have the representation. You see, I can also write no, 0 is this, 0 tensor Vi. Okay, so by uniqueness, all the fxi must be 0. Uniqueness, I must have this for all I. And then I use f is injective. F is injective. So I get xi is 0 for all I. So I see element is in fact 0. Okay. Right. So the point is here just this uniqueness of representations in tensor products. I mean, one of the two factors is free. Okay. So one example, something more concrete, is the polynomial algebra. Yeah, what happens? Okay, polynomial ring over A is a free A module. Polynomial ring AX over A is free A module. Okay, since it is a flat module, since it is free. Sorry, I'm confused today. These technical problems make me confusing. Since it is free. Okay, again, I have this polynomial ring as an A module. It's free. Okay, we know a basis. The basis is given by the monomials, right? So it's free, therefore it's flat. Okay. Right, and what I have another example. Yes, the standard example, kind of. So there was this bad example where we lose injectivity. I can rephrase now. I present it in more generality. It's always the same example in a way, but let's do it in more generality. So let's assume A is an integral domain. Let A be integral domain, M A module with non-zero annihilator. So it will have torsion, the annihilator of M non-zero. Okay, M has torsion. So whenever I have this, then M is not flat. Okay, whenever you have torsion, you don't have a flat module. And why? Okay, very easy. I take an element in the annihilator, a non-zero element. Such an element exists by assumption. Okay. Right. And then I'll look at the inclusion. Consider inclusion of the submodule. I have AA. It's a submodule of A. Okay. It's the, yeah. This principal ideal generated by A is an ideal in A, is a submodule. The map is the inclusion. And now what happens if I tensor with M? With the identity of M. Okay, then this goes from here to here. Okay, but I know A tensor M is canonically isomorphic to M. I just write equals M. Okay, with the understanding this equal is a canonical isomorphism. Okay. Right. Now let me check that this is not injective. Okay. So what do we take? So we apply this to this element AV tensor X. X is in M. Okay. Let's see what we have. So this is sorry. What do I want to do? Yeah, this is okay. AB tensor X. So this is AB tensor X. Okay, it looks because F is the inclusion. But now I can move over. See this A, I can move to the other side. I can move it here. Now I'm here. Maybe I put parentheses. But AX equals 0. Okay, because A is in the annihilator. So this is 0. Okay. But maybe, yeah. So F tensor identity in M is the 0 map. Right, but maybe let's check that indeed, okay? But this is non-zero, okay? Maybe let's also write this. Okay, but this one, this is not the 0 module because I know why, okay? Because I know this is isomorphic to A. Maybe I should write separately. This is isomorphic to A since A is non-zero and A is an integral domain. So, right, the map sending say B to AB is injective, okay? So this is isomorphic to A tensor M. But A tensor M, we know this is canonically isomorphic to M, and M is non-zero. Hopefully I assumed that. Yeah. So, okay, so I'm done.
Can I ask a short question?
Sure.
When we defined torsion, we said that there exists an element in M that has non-zero annihilator. But here we assume that the annihilator of M is non-zero. Is this the stronger condition? So are there modules with torsion that are flat? Or is it equivalent?
Good question. I think it depends on the ring. I don't think that what you're saying would be true over any commutative ring, but over certain ring is certainly true. So for instance, okay, one example, say if A is a principal ideal domain, okay, like the integers and, you know, polynomial ring in one variable over a field, then this is true. I mean, the only property that destroys, then you can show a module is flat if and only if it is free, if and only if it doesn't have torsion. Okay, but it's not true always. There is also a class of examples. Say you have a local algebra. A local algebra. I think, yes, local is enough. I think there one can prove flatness and being free is equivalent. Okay, but this requires a little bit of work. It's not too hard, but okay. So in many cases, I think probably it's a good idea if you want to think what does flatness mean. If you what you have in mind is free. I think that's a good proxy. But there are some cases where this is not true.
Okay, and what about torsion? Are there modules with torsion that are flat?
Well, you see, okay, then, but what I just showed is if A is an integral domain, then this is impossible. Okay.
But, yeah, that's kind of my question, because
that's the question. The question is, how about this? Okay.
No. The question is, here we say the annihilator of M is non-zero, but torsion we define that there is an element in M that has non-zero annihilator. And it seems to me that the annihilator of all of M being non-zero is kind of stronger than
that's the
annihilator of a single element. And I was wondering if this is an equivalent definition of having torsion, or if it's stronger, and if there can be a module with one torsion element, for example, that is flat. But if this is
module,
too much of a digression, I can wait.
Okay, that now I understand. But wouldn't that proof that I just showed you show that this is not the case? I mean, I'm still a bit confused about.
Well, we need it for all x and not just for one.
So maybe I'm not sure. Let me think about it. So maybe maybe I can return to it. Yeah.
I mean, the proof, even if it just held for one x, then F would still not be injective. So I think we can only argue that F tensored with the identity is the zero map if the entire module gets annihilated by some element of A. But if it's just that M has torsion, so there's one element X that gets annihilated by A, then the proof still shows that F tensor identity is not injective, but it's not necessarily the zero map.
But it's not injective, yeah.
Yeah.
Right.
Yeah, so we
I
actually
think you are
assume
right.
more than
Yeah.
we actually need here.
Yeah, probably there is a stronger assumption that we actually need it.
Okay.
Yeah. But maybe I can put on the exercise sheet something that explains this a little bit more. Okay, I understand. Thank you.
Thank you.
Thank you for the question. Okay. So anyway, my plan is, because I'm a little bit behind my schedule, to skip several things that I usually discuss. Right, let's move on directly to the next topic, which is tensor product of algebras. So I admit this whole topic of flatness, I mean, you can talk about it quite a long time. So if you, for instance, if you go to Bourbaki, I don't know, Bourbaki commutative algebra. Okay, it's kind of a strange book. It's encyclopedic, but it starts with the tensor product. And there is, I mean, the whole half of the book, at least, even more, is just about tensor product and these properties. But okay, I'm not going to do that. So let's move on to a new topic. Maybe I can say more about this flatness in the exercises. So it's tensor product of algebras. Okay. So what is an algebra? So what is an algebra? Okay, definition, recall. Or what would you say? What is the definition of a commutative? What is the definition of an algebra?
It's a field inside of a ring.
Can you say it again? I did not hear it. It's too not loud enough.
Maybe it's a ring that contains a field.
That would be an algebra over a field, okay? But what would be an algebra over A? Let's say we are now more general. Instead of a field, I want to have an algebra. A is like what usually takes the role of the field.
Well, I would say a module over A, which is also ring.
Yeah, good.
Where
Yeah, correct. But there needs to be some compatibility or no?
Right.
Or...
So I guess like distributivity between the
Yes.
Well, the ring structure needs to agree with the module structure.
Yes, this is 100% correct. But there is an even more elegant or concise way of defining it.
Maybe just a ring morphism.
Correct. Very good. So it's just this. Let's say F from A to B be a ring morphism. When I say ring, I mean commutative ring. Okay, that's it. Then this is the whole thing. Then now we have two things. On the one, now I'm thinking of B. Okay, B should be an A algebra. B is a ring, but this A module structure I also have. So I have A module structure on B given by AB. It's just this. By the way, the connection is now good. No disturbance and nothing. Better. Okay, so maybe it was the initial problem at TU. Now it can work. Okay. So this is the right. I have this A module structure. And so in a way, you can also say this A module structure is the scalar restriction of the B module B. Okay, it's just another fancy way of saying it. And this is the scalar multiplication is compatible with the ring multiplication. Is compatible with ring multiplication in B. Obviously, that's the way I define it. Okay, and we call, this is the definition, we call B an A algebra. That's it. So it's just a ring homomorphism, okay? Or, I mean, you can say, so, okay, A algebra Okay, this was the elegant way. Now, okay, algebra is a ring B together with the ring morphism. So that's the characterization. That's just a concept. Okay, and then, okay, some examples to explain the concept. First, if A is a field, I think, so then you can think of this F as being injective. So more precisely, if B is non-zero, which is otherwise it's completely boring, then this canonical morphism is injective. And now, and so I can view K as a subring, okay? Okay, it can be viewed as subring of B. Okay, so then you have a ring and the subring, which is a field. But in general, I mean, maybe you don't want to have injectivity all the time. Okay, so you can also say you have the integers and you reduce modulo and ideal. So okay, let's say A is the ring of integers. Okay, so what is now a Z algebra? Well, it's just a ring. Okay, for any, there is no additional information for any ring B. Okay, maybe there's exactly, I save some writing, there's a unique ring morphism from the integers to B. Okay, so Z algebra is the same thing as ring. Okay, let's write this here. Okay. So, and what is a morphism? Now let me define what is a morphism of A algebras. Okay, what will it be? It will be a ring morphism, which at the same time is A linear. Again, it can be phrased maybe in a more elegant way with this homomorphism. So if F from A to B and G from A to C are ring morphisms, okay, then an A algebra morphism okay, is a ring morphism. Okay, H from B to C such that now comes this commutative diagram such that, okay, so this is F and this is G and now it goes here. Okay, such that this is a commutative diagram. Okay, so it's exactly, this expresses the compatibility of the A module structure, I think. Yeah. Okay, it's all completely natural. Okay, so I have okay, this example. Yeah. So what is an algebra? So A is a ring, and then I take the polynomial ring. Okay, I take the polynomial ring over A in one variable X. So what is an AX algebra? So which kind of data do I need to define an AX algebra? Well, this is nothing. It's a ring homomorphism, say from AX to C. It's a ring morphism by definition. And this, okay, this corresponds to, bijectively corresponds to, on the one hand, I can just restrict it. I have a ring morphism from A to C. And then I say, what will be the image of the variable x? So I have an addition element C. So maybe if I call this phi, then this C would be phi of x. Okay. So once I have a ring morphism and I pick any element here, I can say x should go to that element and then it extends. Okay, so it's exactly that. Right. It's like if I would say, what is an algebra over kx, k a field? Okay, what would it be? Did I want to say? Yeah, it's a K algebra. And yeah, okay. I think I don't have more to say. I cannot explain it better. Okay, so in connection with these algebras, there are some notations that sometimes it can be a little bit confusing. So let me explain these namings. It's finite type and finitely generated. So one should not mix these things. So definition. So a ring morphism F from A to B is of finite type. Okay. So if B is a finitely generated A algebra, if B is finitely generated, A algebra. Okay, so I can say it in more concrete terms. That is, there is a subjective A algebra morphism from the polynomial ring. So here I have the polynomial ring over A in finitely many variables. And I go to B. Okay, subjective. Okay. Right, so this exactly means B is finally generated as an A algebra because, yes, these variables are just the inverse images of the generators. Or I can say every element of B is a polynomial. Yeah. Okay, let me write it. Means there are elements. Now I write them in small letters. They are in B, while the x's above are variables. They are written in capital letters. So it means there are x1 up to xn in B, such that every element in B can be written as a polynomial in x1 up to xn with coefficients in A, such that every element of B can be written as polynomial in x1 with coefficients in A. Okay, this means of finite type. Okay, but right. Sometimes we say the ring is finely degenerated. A ring is finely degenerated if it's finely generated as a Z algebra. It's the same. If it is finely degenerated as a Z algebra. So there is nothing happening here. It's just this definition of getting used to the definitions. Okay. But you should be careful. There is also the notion of finiteness of ring morphisms, and it means something completely different. So warning, okay? So maybe this is maybe a reason. go in detail. Okay, there is another definition. Okay, a ring morphism f from A to B is called finite. Maybe I put it in yellow. Finite. Okay, not finite type, finite. If B is seen, if I view B as an A module, so I do scalar restriction, then B is a finally generated A module. If B is a finitely generated A module. Okay, so this means I have a finite list of elements. I call them again x1 up to xn in B, such that now every element of B is a linear combination of x1 up to xn with coefficients in A. That every element of B is a linear combination. So the coefficients are in A. So you see here I require, it's much a stronger condition. Above, I mean the element in B is okay to write as a polynomial. So I could have x squared plus x2 or something. Down here, it should be a linear expression in the x's. So this leads to this remark giving one implication. So if f is finite, then in particular, f is of finite type. Okay, but otherwise, but the other direction is false. So any example why? Can you give me an example which shows that
Maybe the inclusion of k in the polynomial ring.
yes, that's exactly this is the, yeah, I wanted to do it right. This is exactly this. So this is of finite type. Okay, because clearly the polynomial ring kx is finitely generated. It's generated by x, but it is not finite because kx is not it's not a finite dimensional k vector space. Okay, right. Okay, so okay, there are these just these namings. So, but the topic of the section is tensor product of algebras. So let's define what is the tensor product of algebras. Define now tensor product of algebras. Of course, I will do it in full generality. I talk about algebras over the ring A. Okay, so I will have two algebras, and then I define the tensor product. So the algebras are A algebras are ring morphisms. So I have F from A to B and G from A to C. These are ring morphisms. They give me the two algebras. Okay, so what will I do? First I can form the tensor product when I view B and C as A modules. Of course, these are A modules. So I take this tensor product, I call it D. This is the tensor product of B and C. Okay, maybe I put A here as a module. There's a module over A. But now what I need to do, I need to define a ring structure. So I need to define a multiplication on D. Okay. Okay. So how do I get the multiplication? Okay. Of course, it should be something like, so what do I want? Yes, yeah. Okay, let me just write it and then we'll see. Because, okay, what I want, maybe I can write. I mean, the multiplication should be like that. So maybe this is what I want. So I want this to be this. Okay. So it looks a little bit like component-wise multiplication. This is what I want. Okay. Right. But that is the usual thing. Not every element of the tensor product has this form. Okay, so now I have to, it's the usual explanation why it is well defined. The usual blah, blah, blah. So what I do, I look at this map, a multilinear web. So B times C times B times C to D. And what does it do? B comma C comma B prime comma C prime goes to, here I form this tensor product, then I form this tensor product, not tensor product, just usual product and then tensor product. So the point is this map is a multilinear. It's well defined, and this a multilinear. Actually, it's 4 linear. We have 4 factors. So this is defined. Now, next step is it deduces by universal property of the tensor product, it uses an A-linear map. Okay. So now here, tensor product of 4 factors. Okay, so I hope you see. This is the universal property of the tensor product when I have 4 factors. This is multilinear, so it factors uniquely over such a guy. Okay. I don't have to write the diagram. So this defines now, so how do I do it? Okay. Right. So maybe, okay. This is canonically isomorphic to B tensor D. Because here I can, I can put the parentheses here because the tensor product is associative up to canonical isomorphism, okay? Right? So I have this. And then, right, and here I have this map, D times T goes to D tensor D. I mean, it's also the tensor product map. So if I combine this, compose this, I get this map. So I obtain this way, a bilinear map from D times D to D. I can call it, let's call it mu. This is the multiplication map. Okay, so it's okay, and this characterized by this is exactly what I wanted. B tensor C, comma B prime tensor C prime, mu of it should be this. Maybe I put here parentheses. So that's the way I defined it. Basically, it's just a certain reasoning saying this is well defined. Okay. But the proofs are always the same proofs, okay? Universal property. So, okay, so then straightforward to check. That in fact, that D is a commutative ring. D is commutative ring. Okay, with the unit The unit is just 1 tensor 1, obviously. Okay. Also, I have a ring morphism from A to D. Moreover, I have the ring morphism from A to D. Okay, and what does it do? A goes to FA tensor GA. Okay. And this is thus, so I mean, now, now I see, okay, this T is not only a ring, it's an A algebra because it comes with this ring homomorphism. So thus, T is an A algebra. This is called the tensor product. Called the tensor product. Okay, of the A algebras B and C. And why can I call it the tensor product? Because this is unique up to canonical isomorphy. So I have, again, I have a universal property. Let me phrase it. So I have a commutative diagram. Okay, so on the one, so this is how I started. This was one algebra, and here is the other one. Okay, this was like given, and now what I constructed, I constructed the D, and this D comes with two maps. Okay, what are these maps? Let's call them U and V. What do they do? U, sorry, U of B U of B, what will it be? It will be B tensor 1. And the B of C, it will be 1 tensor C. So in a, I wouldn't say that okay, it's not that I embed, maybe, okay, it's not that I embed B in D. I don't say that the U in injective, okay? But I can interpret the element B in D by viewing it this way. And the same, the C, I view this way, okay? And this is a commutative diagram. So this is a commutative diagram because, yeah, let's write it, why not? So commutative. Okay, why? So what do I have to do? Okay, I have the element A here. Then I have here FA. Then I tensor it with 1. So this is what I just wrote. Here is A. Here is F of A. And here is F of A tensor 1. Okay, but also works the other way around. So how do I do this? So, okay, so actually the claim, let me put it as a claim. So then you see what I want to show. The claim is this equals 1 tensor G of A. This expresses the commutativity of the diagram. And how do I prove it? So it's a stupid proof. Nothing is happening basically. Okay, this is, instead of F of A, I can write F of A times 1. Okay, and then I say F of A times 1 is A1. This is how I define, okay, my B becomes an A module by this definition. So this is the definition of the A module structure on B. And then, right, now I have this tensor product of B and C as A module, so I can move the A to the other side. Okay, this is the tensor product of the modules. Okay, and then it's just, then I say A of 1. This is actually, how is it defined? This is G of A times 1. because here, this A times 1, this is why, or the how C is an A module. And that's the way I define the A module structure. Okay. And finally, okay, of course, something times 1 is this something, so it's this. Okay. So, and what is the universal property? Okay, for each commutative diagram of rings. So, okay, so I start with this and this. These are my two algebras, F and G. Okay, now, okay, we have this diagram here. Now let's assume I have, instead of D, I have another, maybe, what is a good color? Violet. I have a D prime. A algebra is an A algebra coming with two morphisms, U prime and V prime. Let's go this way. This is commutative. This is a commutative diagram. Then the statement is, maybe, let me put in here the D. This is U and this is V. The point is there is exactly one, maybe put in red, there is exactly one ring morphism here making the diagram commutative. Let's call it V. So there is exactly one W from D to D prime ring morphism such that the diagram here is commutative, and this would express first W, no, first U, then W is U prime, first B, then W is V prime. It expresses commutativity. Okay, very abstract, I know, but this is characterization of tensor product of algebras, like in terms of diagrams. Okay. Of course, this now one would need to prove it, but the proof is straightforward. I hope you understand. This is, I don't know. There is another part of mathematics. I think when I first encountered this kind of mathematics, it was, I don't think it was even here. I think it's in differential geometry. It's just, you have these definitions. I mean, it just works. It's like a machine. Okay, you prime will do tuck tuck tuck. Yeah, you just have to check, did what I write, does it make any sense? And you understand when it makes sense, then often that's what it is. So it's here it's a little bit similar. So we need to prove universal property, but of course it follows from the universal property of the modules. You just have to check the details. Okay. Other, yeah. Or maybe I should write, okay, there's one thing we have. Okay, the commutativity. This looks a bit strange, but it means commutativity means, okay, this funny thing concretely means this, W of B. Okay, the B tensor C isn't a generator, it's an element of this. What we want to have, this should be U prime of B tensor B prime of C. So this is what we want to have. Like tensor products go to tensor products. Is there a question on that?
Yes, you said that the map U doesn't have to be injective, or that you don't claim that it's injective. But I wondered if there could be any case where U would be not injective. So tensoring with an element, like is there any any way to tensor?
Let's see. Think of right, but think of the situation of modules. So, okay, good question. But we had this example. Maybe I put it here. When we looked at Z modules. So you remember this? Okay, and there was this extreme case that this is 0 if the GCD, if they are coprime. Right. So can't we say that this, okay, now, okay, A, let me put, so A, so this is the example where A is the integers. So let's call this B, and this we call C. We know these modules are also rings. Then let's form the tensor product. I mean, how do you do it? You form the tensor product as modules. You get 0. So this is an example. Okay. It can happen.
Yeah, okay,
it
but
can happen. Yeah,
it's very strange.
Yeah, it's strange. Yes, but it's okay. If you don't like it, in fact, it's extremely useful. If I can give you a life an advice, how do you say, gute Ratschlag, an advice. It's better you like the tensor product, even though this behavior is really strange and it may look pathological. It's in a way, it's a feature. It allows to express so many things. So it's a good thing, but you need to get used to it. Okay, I wanted to give one example. An example, I think we had it already. I think we had scalar extension. So, okay, it's not too interesting, this example, but so what did I have? I think I had a ring morphism from A to B. Then I looked at the polynomial ring, and then what I did was the scalar extension. The scalar, so I turned this into a B module by doing this. And then we showed that canonically, this is this. Okay, this was a scale. Okay, recall scaled extension. Okay, I did this example, right? What I want to say now, when we discussed this, we were just talking about modules, but this is also makes sense in terms of rings. Okay, so this tensor product, maybe I showed you. Okay, this is true, not only as A modules, but also as A algebras. Okay, and this is again trivial to check. If you say B is an A algebra, AX is an A algebra, I form a tensor product I get an algebra, an A algebra, and it's that one. Of course, it's the way we define things. Okay. So, right, I think I can. Okay, maybe this can be an exercise. Maybe it shows that the tensor product is useful. It's another example, basically. So, right. So consider A algebra. Okay, and I is an ideal. Okay. So, right, it's about reasoning what is the scalar extension, but basically it's reasoning about tensor product of algebras. So let A to B be a ring morphism. Okay, so I have now B as an A algebra and I have C as an A algebra. Okay, what is the scalar extension? Okay, what is the scalar extension? Of C. Concretely, I mean, we know what it is. I mean, 3 sec to B, okay? Okay, maybe I can write. Sorry. Right, the scalar extension, I mean, abstractly we know, okay, of C. Okay, we would write it B. Okay. Okay, this is just a symbol. And the question is, but what is this object? Can I describe it in more concrete terms? Right? So you can think of it as an A module, but you can think of it as an A algebra. Okay, and there is this statement. Okay, I think, let me put it as a lemma, but I want to put it on the exercise sheet. So that says I have a canonical. Okay, canonical isomorphism of A algebras. Okay, so on the one hand, this is the scalar extension, this tensor product. Now I want to write it in a simpler term. I mean, the result should be, because I have a scalar extension, it will be even a B algebra. But what will it be? And it's okay, it's the most natural thing you can think of. You get it as a factor algebra of the polynomial ring over B. And what do you factor off? It's just the extension of I in the bigger polynomial ring. It's this. So this is the ideal generated by I in Bx. Okay, so you see this factor ring has the same structure as this ring. So in a way, instead of A, you have to say B. Okay, wer A sagt, muss auch B sagen. Instead of A, you say B. I mean, in the coefficients, and then you have it. Okay. So let's do this as an exercise. Okay, I will make the suggestion to Marco. So in a way, it says that this tensor product behaves nicely in comparison with factors. Okay, on the one hand, you form factor rings. On the other hand, you have this tensor product of algebras, and it behaves nicely. Right. You see, I mean, here, first, okay, I form the factor ring, then I do the scalar extension, then I do tensor with B. And here, first I do tensor with B, okay? Maybe I should write, maybe, sorry, maybe, okay, maybe I should have said this before, or, oh, here it is. Sorry, it's okay. Here's what I said here, okay? If I take the scalar extension of AX with B, I get BX. Then you see what we have here. We first did the scalar extension, okay, but we also do it for the ideal, and then we take the factoring. So these two operations commute. Okay. More questions or?
I have a question.
Yeah.
I don't know, maybe turn off the recording if we are stopped, or?
Sure.